we have any questions about the quantum theory? Electron configuration and quantum mechanics, or principal quantum numbers? You good? All right. Today we're going to talk about periodic table trends and polarity a little bit. You guys know what a trend is? What's the trend these days? Anything goes? Pretty much, right? I just want to share you this picture because I think it's funny. Anybody into Air Jordans? Okay. Is this a single pair? What is this? They are identical. Minus this one's older, right? You can see it's a little discolored because of its age, but well, it's probably just they had budget cuts, I don't know. So let's just use the same one in 1985. Those guys are all oldies. Let's give it to their kids, and then they're going to be made fun. No, no, that's. But this is way in style now, right? Back when I was a kid, this is what the style was. Crazy, but things change and whatever. So trends. Does everybody have to follow the trend?
No.
Does everybody follow it anyway? No. So when we talk about periodic trends, this is not a solid, cold-cut line that it has to follow. But this is just to kind of help us to kind of make predictions of what might be. Okay? So we're going to talk about probably just two trends specifically. So atomic radius. What does atomic radius refer to? You guys know what radius is? Yeah, so if we have a circle, it's from the center of the circle to the outside, right? That's the radius. What's the center of an atom called? The nucleus. The outside of the atom called? Valence electrons, right? So the distance from the nucleus to the outer shell. That's the atomic radius. Basically what we're talking about is the size of the atom. So let's take a look at this trend. I'm going to pull up a periodic table here. As we go from, let's say, top to bottom, what happens to the atomic radius, would you guess? What? Larger, getting bigger? Why is that?
It has more everything.
More shells, right? So it gets larger. Does that make sense to everybody? Okay, so it increases going down. What about from left to right? What happens to the number of shells if we're going from, let's say, lithium to fluorine? More shells, less shells? Same. Energy level 2, N equals 2, right? For both of them. So we can't say it's bigger or smaller based on its number of shells. So what do you think? Does it get bigger? Does it get smaller? Stays the same. It looks like it stays the same, right? Okay. But let me, it doesn't stay the same. It actually gets smaller. It decreases. Let me tell you why. So if we take lithium, for example, what is attracting those electrons in lithium? The nucleus. And what's the charge of the nucleus? 3. Has 3 protons, so it's plus 3. Pulling in those electrons. You with me? And we go to fluorine. This has a plus 3 charge. When we go to fluorine, it has a plus 9 charge. Who's going to pull these electrons in tighter and tighter and tighter? Fluorine, because it's stronger, right? Pulling them in tighter and tighter and tighter, making it smaller and smaller. A lot smaller? No. But smaller. Okay? Now there's one thing we're going to learn is effective nuclear charge. So if we said Z, do you remember what Z is? Like in the form, this one here. The Z is the number of protons, or the charge of the nucleus, right? So that's the charge of the nucleus. But that's not the charge that really pulls these electrons in. We got to look at something else. And we call it the effective nuclear charge. So Z effective, EFF, that's the effective nuclear charge. And why would that be different? On that first energy level, are those inner electrons doing anything? They're repelling the other electrons. You with me? So to find the effective nuclear charge, this is equal to the number of protons an atom has minus the shielding number of shielding electrons. So if we draw a Bohr's model, I like Bohr's model because it's simple. So we got 2 electrons on that first energy level. For fluorine, for example. How many do we have on the second energy level? Look at your periodic table. 7. 1, 2, 3, 4, 5, 6, 7. Okay? So we have 9 is our nuclear charge minus the number of shielding electrons. These ones right here are shielding the proton, right? The protons. They're kind of pushing the other electrons out, right? So we take those away, and we get positive 7. You with me? Yeah.
So the shielding electrons are just all of the shells before the outer shell?
That's right. Good. Thanks for asking. And if we look at lithium's effective nuclear charge, what's its nuclear charge in general? Positive 3, right? And how many does it have on what's the shielding electrons?
2.
Just 2. Just like fluorine, right? So that's a positive 1 effective nuclear charge. Either way, it's a bigger charge for fluorine, right? We'll use this a little later too. Does everybody understand that idea? Let me do an analogy. Yeah.
So
Milosh.
then is the effective charge always going to be equal to the number of valence electrons?
Good question. Not always. Depends on if it's charged or not,
Oh yeah.
and if it's a transition metal,
Right.
right? Okay. So let's say we have two magnets. I'm gonna just use other object. These are magnets. You like my magnets? Okay. Okay, we'll say this is a fridge magnet. You guys know the fridge magnets has letters and stuff and whatever. Okay. And this is a neodymium magnet. You guys know a neodymium magnet? It's a rare earth magnet that's really strong. And if you play with them, you might get blood blisters. Right? You ever see these magnets? They're very strong. Okay. Huge, strong magnet. This is like fluorine. Has a nuclear charge of +9, or we could say an effective nuclear charge of +7, right? And this is like lithium, has an effective nuclear charge of +1, weaker magnet. Since they're at the same energy level, where do the electrons want to go to? The outside, right? That's where they are, the outside. So this electron, am I trying to? No. I'm trying to talk about something else. Sorry. Let's wait. I apologize. Got a little ahead of myself. Sorry about that. But do you guys understand that it has a stronger pull, so it's going to pull those electrons, those outer electrons, in tighter and tighter and tighter. Yeah? Do you understand that okay? All right, so let's do an example. We have oxygen versus sulfur. Which one is larger? Sulfur is, right? Why? Same number of valence electrons, but higher energy levels or shells, right? So more shells, so it makes it bigger and bigger and bigger. So this one's larger. What about the effective nucleus, or the effective nuclear charge for these?
It's the same.
Oxygen's higher, right?
Well, let's figure it out. Let's find out. So what's the, so it's Z minus the number of shielding electrons, right? So what's the Z for oxygen? 8 minus how many are shielded? How many electrons are shielding the nucleus? 2. So that's a +6. What about for sulfur? 16. How many are on the inner energy levels? 10. You got 2 on the first energy level, 8 on the next one. You with me? That's shielding that electrons. They're not the valence electrons. So -10, we get +6. We good? So if they're in the same group, they're going to have, if they're neutral atoms, they're going to have the same effective nuclear charge. You with me?
You have ZEFF and then EFF.
Oh my gosh. What? Well, what's wrong with that? Okay. Sorry. Thanks for setting me straight there. if I want to do that example, because that's not a very good example. What about, oh, that talks about something else. I'm going to confuse you guys if I'm not careful. What about sodium and chlorine? Which one is larger, sodium or chlorine? Chlorine's larger? What do you think? Should we find the effective nuclear charge? Did I do it right that time? Okay, so what's the effective nuclear charge for sodium? 11 minus.
1.
Is it just one shielding electron? Oh, you're saying it's positive one, right? Yeah, so there's 10 shielding electrons, that's positive 1. And for chlorine, it's 17 minus also 10, right?
That's the next one.
So this is plus 7. You with me? Did you have a question?
Plus 7. I thought the number to the right of the equals was the charge.
We're not talking about the charge.
Oh, it's not charge. Okay.
Nope, we're talking about the effective nuclear charge. So the charge of the nucleus, which is always going to be positive, right? No matter what atom you're talking about, because it's protons only. So since this one's bigger, does that mean it's smaller? What do you think?
Radius-wise?
Yeah, this one's on energy level 3. This is on energy level 2.
Yeah, it's bigger than.
Yeah, it's larger. So you got to look at how many shells it has first before you look at the effective nuclear charge. Good? Any questions on the atomic radius or the size of the atom?
Wait, sorry, can you say what you just said again? Why do you have to look at how many shells there are
Because
before you look at it?
if we have, for example, here's sodium, has 2 energy levels, right? It has 3 energy levels. Has 1 electron on that outer shell, right? And for chlorine, 1, 2, hold on.
There's 3 as well.
Oh! This is why you always use the periodic table, ladies and gentlemen. It also has 3. Okay. Good call. Thanks for asking. Thanks for stopping. So they have the same number of energy levels, same shells. So it appears they're the same size, but since chlorine has a larger effective nuclear charge, then which one's larger?
Sodium.
Sodium is larger. If it has a greater effective nuclear charge, it's pulling those electrons in tighter, and tighter, making it smaller and smaller and smaller. You with me?
Yeah, until you add the next shell, which increases. the
Yeah.
radius a lot.
In my mind, I was thinking chlorine was on that next one down. Sorry about that.
Okay, that makes sense.
Okay, questions. Let's make sure we're clear before we move on, because I just flubbed that one up, didn't I? Okay. So what are our questions? Should we do another example? Yeah.
So then sodium is larger because it's not pulling the electrons?
Yeah, it's the same number of shells, so they both have 3 energy levels, right? So they appear to be the same size, but since chlorine has a greater effective nuclear charge, it's pulling those electrons in tighter, and tighter than sodium is. That makes chlorine smaller. So sodium is larger than chlorine. Good? Any other questions?
Can you explain once again why chlorine is pulling it in tighter?
Do you understand
Because it has
effective
a
nuclear
higher
charge? Effective nuclear charge. right? It's pulling those in tighter and tighter, making it smaller and smaller.
So like the higher charge, the smaller the size?
Yeah, but do you understand why? Because if we just remember, okay, just if the number's bigger, then it's smaller. That doesn't make any sense in our mind, right? So just remember, if it's kind of like the big magnet and the small magnet. If you have a big magnet in the center, it's going to pull those in stronger, more strongly, right? A smaller magnet, not as strong. If it's pulling it in with the stronger force, it makes it smaller. Yeah, Olivia.
Even in the previous example, they both were +6, but because the subshell is higher for sulfur, that's why it's larger.
That's right. So you got to check the number of shells first, or the N, the shell number. Has a larger shell number, more energy levels, it's going to be larger, hands down. Because this difference in size for sodium and chlorine is not huge difference. Not a huge difference. But it is a difference, yeah.
So going back to like your magnum example, are you thinking like because the protons are in the nucleus, there's a positive charge in the nucleus, and a larger negative charge on the outside wants to attract positive and negatives in the nucleus so it condenses it?
Well, yeah, the electrons are negative, good. Nucleus is positive, so opposites attract, right?
Right, so the more electrons on the outside, the stronger the attraction inwards will be to the positive center?
It's not the number of electrons on the outside. It's the number of protons on the inside, or not just protons, but the effective nuclear charge.
Okay.
So if it has a stronger pull, because the nucleus is going to try pulling those electrons on all of the atoms, right? They're all going to have a pull. But if you have a stronger magnet on the middle, then it's going to pull even tighter. It's kind of like if you understand planets, well, you have the Earth and the Moon. You go to the Moon, you're pulled to the surface of the Moon, right? There's gravity on the Moon. You guys understand there's gravity everywhere, right? Okay, there's gravity on the Moon. There's gravity on Earth. Which one are you pulled in more strongly? The Earth or the Moon? The Earth. It has a stronger pull. Why? Because it's more massive. It doesn't have more charge, but that's kind of what we're talking about. Chlorine has a bigger charge, kind of like the Earth compared to the Moon. You with me?
Yeah.
Or did that just kind
That
of...
makes sense, and like bigger planets pulling like more moons.
It's pulling in tighter and tighter, but... and again, is it a lot smaller? Is chlorine a lot smaller than sodium? No, it's not. And if you look it up online, you could probably find values which are in 10 to the negative values, right? Negative 10 values. But anyway, that is the trend of the periodic table. Are there some that might not follow that trend? Sure. Okay? We're not going to talk about those, but there are some that might not follow it. But this kind of helps us to have a good general summary of what happens as we go up or down the periodic table, left to right. Okay? Any other questions? Yeah.
Yeah, like how much greater is the radial difference between a new shell versus what changes along the same period? You know what I'm saying?
I couldn't tell you a number, but
It's like very marginal.
it's quite a bit bigger if it has an extra shell versus more nuclear charge.
Okay.
Okay, so that's the first step is which one has a bigger shell, more shells, right?
Yeah, so something close to a noble gas will never be even close to the radius of something in the very next period at the beginning. Sorry.
Yeah. So like if we look at sodium versus fluorine, are you talking like that? Sodium versus fluorine?
Yeah, exactly.
Yeah, so fluorine has a greater effective nuclear charge, but sodium has an extra energy level. So it's hands down bigger.
Right.
Well, it's going to be bigger anyway because it has a less of a nuclear charge. So
Yeah.
either way, Victor.
Sorry, I'm still playing catch up a little bit here. Z is our atomic number.
Uh-huh,
That's
uh-huh.
fine.
That's
How do
the
you determine
charge of the nucleus. So
charge of the nucleus?
Uh-huh.
Yes. How do you determine the number of the shielding electrons?
okay,
That's, minus 10.
so on sodium, it has 2 electrons on that first energy level, right?
Yep.
Has 8 on the second energy level, and 1 on the outer energy level. So these guys, so the only electrons that are not shielding electrons are the valence electrons.
Oh.
So we have a total of 11 electrons, right? Or sorry, we're not talking about electrons, we're talking about the protons, right? So it has a charge, a nuclear charge of 11. You with me? And why are these guys shielding the electrons? Why are they shielding that electron? Because electrons do what to one another? Repel each other. So we got repulsion going on. But we also have we have, on this one, we've got a positive 11 in our center that's kind of pulling everything into it, right? But you also have a negative 8 that's kind of, well, not 8, 10, sorry. You got a negative 10 charge from the electrons that are kind of pushing against it. Does that make sense? Pushing against this electron right here. And so that's why we take 11 minus the 10, and that's going to give us a positive 1 effective nuclear charge. So basically, it's a weak magnet, right?
Can we go through that same logic but for chlorine now?
Yeah. So chlorine has 2. And again, you can just use the periodic table. You don't have to draw this, right? But it also has 7 on the outside. So it has 17 total protons. You with me? Because its atomic number is 17. And we're going to subtract the inner electrons. Everything but the valence electrons. That's a total of still 10. And that gives us positive 7. So it has a greater effective nuclear charge. Yeah? Did you have a question, Liana?
I answered it.
Okay, perfect.
If you think about it, it was a dumb question.
No such thing. Well,
Can you ask it anyway, because it might help me?
there are such things as dumb questions, but you guys haven't asked one yet.
Basically, what I was gonna ask is like, is there a scenario where the shells, basically what matters more is
The number of shells.
matters more than the pole.
Yep.
Which obviously,
Yeah.
if you think about it, so that's.
Yep, because if it's further out, think, and here's why. I'm glad you're asking this, because now let's talk about why. The electric force, the electrostatic force. We get a balloon and rub it on our head, right? We put it to the wall. If I just hold it right here and I let go, what's going to happen? It's going to fall. If I get a little bit closer, maybe halfway between me and the wall, and I let it go, what's going to happen? Fall. Where do I have to get this thing for it to stick to that wall? You got to touch the wall, right? Got to have it right on the wall. That distance plays a much bigger role than the charge. What if I charge it just so much and my hair's off like this now, and I hold it right here, what's going to happen? It's going to just fall. It doesn't matter how much charge it has because it's so far away. Same thing when you look at the mountain, right? You look at the mountain, it's so far away. It's like, oh yeah, that mountain's about this big, right? You guys can understand what I'm doing here? I can see that clock is this small. Is the clock this small? No. it's like this big. Oh, look at that. That's small. Oh, as it gets further and further away, it looks smaller and smaller and smaller, right? Same thing with that electric charge, electric force. Here's the equation. You don't have to know this. Where Q is the charge, so you have to have two charged objects for it to attract, right? The bigger the charge, the bigger the force. But what happens to the distance? It's divided by the distance squared, which is much, much bigger change. Does that make sense? Okay. You don't have to know that. But it's physics that explains all of this stuff. Yeah.
Can we go over something larger, like uranium or something like that?
Yeah. Uranium is huge because it has so many energy levels. But what about its nuclear charge? Its effective nuclear charge. Look at uranium. Good. Is that? No, I'm not going to draw it out. Because even for the smaller ones, I wouldn't draw it out. I would just look at the periodic table and count how many are shielding, right? So if we look at uranium, this is, well, that one's going to be a little bit more tricky, isn't it? Because you have seven s electrons, and you have six d electrons, and you have 5f. So which one are we going to deal with? Which ones are the shielding electrons, right? I would say anything below 5. But anyway, I'm not going to have you do anything that extensive. But so it has 92 minus the ones in, let's see, in lower energy levels or shells are going to be the 14 from 4F and then 64 plus 10, 74. You guys getting where I'm getting 54th? Look at xenon number 54. All of those are energy level. Oh, that's energy level 5. Hold on. 2, 3, 4, 5. So let's go to krypton 36. So we got 36 electrons. And then we're going to take the 10 electrons from 4D, because that's also 4. So that's 46. Plus the 14 electrons from 4F. 46 plus 14 is 56, 60? Minus 60? So it has a big charge, big effective nuclear charge, but that doesn't matter because it's so big compared to everything else, right? Don't worry about uranium, okay? I don't know if you followed that with the electron configuration type lingo. No? All right. Don't worry about it. Yeah.
I wanted to go back and ask about the sodium chlorine example. The conclusion was that sodium was larger than chlorine.
Yeah.
Why?
Because they have the same energy levels. So that's the first thing that we look at. Which one has more energy levels? If it has more energy levels, it's larger, right?
Oh, makes sense. Yes.
But since they have the same number, they both have 3 energy levels. So now what? Chlorine has a stronger effective nuclear charge, so it's going to pull it in a little bit tighter, make it a little bit smaller. Has a bigger force that's pulling those electrons in.
Okay. So Z effective is larger, meaning it's smaller.
It's going to pull it. Do you understand why, though?
Yes.
Pulls it in tighter and tighter and tighter. Okay.
Did you see
Kevin.
the density of the electron cloud in a way? It's tighter, it's more dense?
I wouldn't use that word because we use that for something else.
Right.
But it's not the electrons
Okay.
that are causing it to be pulled in. It's the protons.
Right.
Okay. Protons are pulling those in.
Mhm.
but you gotta get rid of those shielding electrons that are kind of pushing the electrons out. So you kind of take the charge of the nucleus minus the electrons that are pushing the other electrons out, the valence electrons out, and that's going to be your effective nuclear charge. Yay or nay? Nay. Oh,
It's
sorry.
it's a larger magnetic force, right?
For chlorine,
The,
More-
the,
more
what the
electric.
effective is?
we're talking about electric force.
Oh, it's electric force, not
But
magnetic force. Okay.
I was using magnets because it's the same idea, right? Magnetic field follows that inverse square law just like the electric field, just like light does. Okay? If we keep talking about this, we might get more confused. Okay? But if you have another question, maybe you should ask. Yeah, Danielle.
Could you do an example with ions?
Yes, let's do that. Let's do that. So let's say we have sodium ion and chloride ion, like this. Now which one? Which one? How many energy levels does sodium ion have?
2.
So N equals 2. What about chloride?
3.
3. So which one is larger now? Chloride. You with me? Because it gained an electron and it's still on energy level 3. Sodium lost an electron, now it's on energy level 2.
I was gonna ask sodium has 3 energy levels,
But if it loses an electron, it just lost that valence electron.
yeah, so it just has 3.
Yeah. So what's the effective nuclear charge? Let's do that. What's the effective nuclear charge for sodium ion?
9.
It has, okay, let's see, it has 10 valence electrons now because it lost one. Or sorry, no, sorry, it still has 11, my bad. We're not talking about valence electrons. It has 11 protons, so it's positive 11, right? Still 11. And we're going to subtract the inner shell. How many does it have on the inside?
2.
2. Good. You with me?
Even though the outer shell is complete.
The outer shell is complete. Why? That's why it lost one, so it can be like a noble gas. You with me?
I can't
Question.
for now. Sure.
Well, I see some lost.
Okay, wait, so can you explain again? Like,
Let's do chlorine.
more detail?
Let's do chloride. Let me draw a picture this time. We have the first energy level, second energy level, third energy level. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. That's what chlorine is without a charge. How does it become a -1 charge? It gains another electron. Did it change the number of energy levels? No, it still has 3 energy levels. You with me? Okay, so if we find its effective nuclear charge, so what's the nuclear charge of chlorine? 17. It still has 17 protons. Minus the shielding electrons. These ones right here, everything but the valence electrons. 10. What is it? Still positive 7. Okay? Since this one has a bigger effective nuclear charge, then it's just going to make it even smaller, right? It also has less rings because now it only has 2 rings because it lost one. Whoops. It had one more on the outside, but it lost that electron. Now it has 8 shielding electrons. Or sorry, 2 shielding electrons. You with me?
I think that's where I'm confused, because I'm gonna count 10 total electrons for Na plus, but you're saying it's 11 minus 2?
I'm not talking about electrons. I'm talking about, this is the number of protons. It still has 11 protons, otherwise it wouldn't be sodium. You with me?
Okay, yeah.
And why do we subtract the shielding electrons?
That's positive charge.
Because they're repelling. They're going against what the protons are doing. Protons are saying, come here, come here, come here. The shielding electrons are saying, get out of here, get out of here, get out of here. Which one's stronger? The nuclear charge is bigger, so we have to take the nuclear charge minus those shielding electrons. It gives us the effective nuclear
Right,
charge.
because you lost a ring, so we're subtracting like 2, which is the inner ring now.
Uh-huh.
Not the 8. Okay,
That's right.
That makes sense now.
Good?
Yeah, thank you.
Anything? Yeah, next.
What would hydrogen be?
Hydrogen, yeah. So it has 1 minus, it doesn't have any shielding electrons, does it? So 1 minus 0 is plus 1.
Yeah, okay.
Good? Any questions on the atomic radius or size of the atom? All right, now let's talk about ionization energy. First of all, let's give a definition. Uh-oh. Ionization energy is the energy required to remove a loose electron from the outer shell. And generally, we're talking about a gaseous material, but, okay? Does that make sense, what the definition is? It takes energy to take one of those electrons off, right? We're not talking about putting it on there. We're talking about taking it off. Yeah.
Why are you generally talking about gaseous materials? Isn't it easier to lose an electron from like potassium or an alkali metal?
Yes. Now, this is a trend. Why is it on gaseous? Because that's what it's been tested on. Okay? But you can kind of take this, what we've learned. It's kind of like, no, you guys didn't have that question on the test. Never mind. Yeah. So let's look at the trends. Okay, what happens if we go from left to right? So if we're going from left to right, let's just look at lithium and fluorine, for example. Which one takes more energy to remove an electron? Think about what you already know.
Would be fluorine.
Fluorine takes more energy?
It would take more energy, wouldn't it, because it has 7 valence electrons, so it wants to steal one?
Yeah, it wants one. It wants to take one. It doesn't want to get rid of one, because then it'll be less balanced, right? Yeah.
Is this like with the moon and the Earth example that you put on? It's easier to get out of the moon's orbit than it is the Earth's. That's why fluorine is so much easier to, like, it will take it. Does that make sense? What you're talking about?
You could do
Kind of, yeah. So now here's my strong and weak magnet example that I was going to show you. So here's a strong magnet, here's a weak magnet. Which one's a strong magnet, fluorine or lithium?
fluorine.
Fluorine has a bigger effective nuclear charge, right? Lithium has a smaller one. This is the weak magnet. Now, they're both on the same level, so which one's going to attract it? The strong magnet, right? It's going to want to take those electrons in. So it's going to take more force to pull it off. You guys ever pull a piece of metal off of those strong neodymium magnets? Right? Really hard. And you can do it, but it takes a lot of energy to get it off there. But on a fridge magnet, it's like, dang, not that hard at all, right? Well, if you think about it, we know lithium wants to lose an electron. So it's saying, yeah, it'll help you, right? And fluorine says, I don't want to lose one, dude. Get out of here. And it's going to fight you the whole time. You with me? So what happens to the ionization energy from left to right then? Decreases or increases? It takes more energy to pull off that electron. You with me? So it increases going from left to right. What about going from top to bottom? Is it harder to pull an electron off of lithium or francium? They both want to get rid of one. Which one's easier to pull it from? Here's francium, strong magnet. Where's the electron you want to pull off? Right out here, clear out here. Easy to take off because it's not even close to it. But if you have here, and here's an electron, oh, it's really close. It's going to take more energy to take that one off, right? You with me? So it decreases. The amount of energy it takes decreases as you go down. Does that make sense to everybody? Okay. Now, there are some weird things going on. So we say this is a trend, right? But what about between, let's take nitrogen and oxygen. Which one is harder to remove? You would think that. You'd think it would take more energy to remove it from oxygen. But here is where writing the electron configuration of the orbital diagram helps us understand this a little bit more. So if we write for nitrogen, it's 1s, 2s, and 2p. You with me? And here's oxygen. Also 1s, 2s, 2p. Oops. Looks like that. You with me? All right. Now we have the option to remove that one or remove that one. Which one is going to make it more stable?
Oxygen.
If you remove the oxygen, it's going to make it more stable. Because a half-filled shell is better than a partially half-filled shell. You with me? And so if it's half full, it's going to be more balanced than just partially half full, or a little bit more than half full. Okay? And so if we take this one out, it's going to take less energy in comparison to nitrogen. Is going to take more energy. A lot more? No. But it is going to have a higher ionization energy to remove that electron, because it's already half filled. So you take one away, it's going to make it less stable. Good? So that's a good exception to know about. And when you get into the D level, guys, where's the middle? 1, 2, let's see. 1, 2, 3, 4, 5 right here. So that's half filled. You can kind of use that to guide your thinking. Yeah? Or do we have, yeah, Victor?
So it seems like the best approach is to draw your electron diagram, essentially.
The orbital diagram?
Terminology is not correct.
No,
Can I
you're
just
good.
draw the last shell.
Uh-huh.
Okay, perfect.
Because that's where the electron's coming from. You'll never pull the electron from the inner shells. Always the valence shell. Okay? I'm not going to have you calculate how much ionization energy, but just like on the homework, it says, okay, here's your first ionization energy, second ionization energy, third ionization energy, and so on. What is the second ionization energy? The energy required to take that second electron away. So you have to have the energy for the first plus the energy for the second, right? You with me? Okay. So I won't have you calculate the energy, but you might be given those energies, and you can make sense of what's going on with the amounts of energy that it takes. Yeah, Zach.
So when if you were to take one from nitrogen, like if you were able to, would the electron from 2s shift to fill in the last space on 2p?
No, it would just make it more unstable. But if in case during a chemical reaction, in fact this usually happens during a chemical reaction anyway, but it might do something like that just so that it can be more stable with whoever it bonds with. Great question. Anything else? All right. So those are the two trends we'll talk about. I think I'm going to hold off on the other one because I don't want to confuse you right now. We will talk about it a little bit later, but then I'll give you a table with all those values. So you don't have to worry about the trend anyway. You just look at those values and you got it. But you can't use that on the test unless you put it on your reference sheet, right? Might be a good thing to add to your reference sheet when we get there. Okay, we'll get there. Not yet. All right, any questions about the two trends we talked about today? Yeah, Victor.
I'm curious, what is the application of what we're discussing right now? Like why do chemists care
Okay.
about this?
So if we want to, great question. If we want to know if a reaction is going to take place, for this reaction to take place, this element has to lose an electron. So, well, will it? If it takes this much energy to do it, and is it going to happen? So just to help us predict whether or not a reaction would take place or would not take place.
It's like why we use lithium for batteries, because it's so easy
Yeah.
for it to lose an electron. And that's why they make such effective batteries.
Yep. I know that's not a refined example of where we might use it. But if it has a high ionization energy, then what does that tell us? It would rather gain them, right? So it would be more advantageous to join up with another atom that wants to give some up, for example. Okay. We good? Not solid, but
Yeah, it just seems like, I just don't like chemistry, it just seems like arbitrary rules.
I get it. There probably is a better explanation than what I gave you. Look it up online and see. And let me know.
It's okay, I won't.
All right. Any other questions? All right, isoelectronic. That's the fancy word of saying atoms with identical electron configurations. Okay, so we have magnesium, 2+ ion. What's the electron configuration for Mg2+? What's it like?
Noble gas.
Which one?
Neon.
Neon. So its electron configuration is 1s2, 2s2, 2p6, right? Normally it's 3s2 without the charge, right? We add the charge 2+, that means we lost 2 electrons, and we get rid of that. You follow? So it is isoelectronic, not to sodium, to neon. We good? What about O2 minus? Is it isoelectronic to those same elements? Yeah, it gained 2 electrons and now has an electron configuration like neon. Good? And this is why if we have magnesium, we can just say Ne3s2, right? Then when it loses it, it's just like neon. Are we good with the definition of isoelectronic? Yeah, Quinn.
So, just to see if I'm synthesizing this right in my brain, the formula for the ionic compound or the ionic elements of, or yeah, the ions of magnesium and oxygen are going to have the same like electron configuration as neon.
That's right. These are all the same. Yep.
So in that case, what would oxygen look like with that shorthand?
What would O2 look like, or
Yeah,
oxygen?
Sorry. O2, oxygen 2 minus.
There we go. Right? Yeah.
Is it only in comparison to noble gases, or would you say that Mg2+ is isoelectric to O2 minus?
Yes, these are isoelectronic. Yep. We might not even have this as an example, right? but they're both isoelectronic to neon. Yeah, Nick?
Can they only be identically configured to be noble gases, or can they be for like any element to any element?
Any, like these two right here are isoelectronic.
Oh, okay.
Yes, it can be those two. But they're also isoelectronic to neon, right? Can you have one that's isoelectronic to two atoms are isoelectronic, but not isoelectronic to a noble gas? Is that what your question is?
I think you answered it with magnesium.
Okay. All right.
So like that's going to be argon for S1.
That's right. Yep. Did we talk about the condensed version last time
Yes.
with the noble gas configuration? Okay. Yeah. So that is the condensed version of the electron configuration for magnesium.
That's just regular magnesium, right? Not
Yep.
Okay.
Yep. And how you know? Because there's no charge right there. Yep. Okay. Yeah.
On
Yeah.
the example we be seeing it a longhand or shorthand?
Maybe both. No, both. In fact, if you want to really know, so when I was planning for this, because I didn't write the test, so I just want to make sure I'm teaching you guys the things that are on the test, right? So I opened the test and went through each one. It says, this is what you need to know. Maybe that's too much. Should I not give that to you?
No, for the test.
But this is what you need to know. Now, does it give you the exact problem question? No, it doesn't. It just says, okay, this is what you need to know. Okay? All right, let's do polarity, and then we should be ready to take a break after that. Okay, a polar bond, we talked about covalent bonds, right? What happens to electrons, the valence electrons in a covalent bond? They share, right? So a polar bond is a covalent bond where electrons are shared unequally. Well, that's not nice. But it's life, right? So, for example, we have hydrogen bonded to chlorine, for example. Which one of those elements wants more electrons? Hydrogen or chlorine? Well, maybe that was not a good example for what you know right now. Let's do nitrogen and chlorine. Which one wants electrons more than the other one? Chlorine wants the electrons more. Why?
this higher electronegativity, it wants to fill its.
Did we talk about electronegativity in here yet? That's why. But it's because, well, think about when they make a bond, right? An ionic bond even. Chlorine wants to do what? Just wants one more. Come on, just give me one, right? And nitrogen says, oh, I want 3 more. Who's going to fight harder to get there? Chlorine, because it's almost there, right? It's almost there. But like Gavin mentioned, has a higher electronegativity. So let's talk about that. And I don't know if I have a picture of this. Let's see. All right. So fluorine is the highest, or the atom with the highest electronegativity value. And if we think about it, so fluorine wants one more. So why is it higher than chlorine? Chlorine also wants one more. Well, what's causing that thing to attract? The nucleus, right? Is causing that thing to attract. Well, hold on. Chlorine has a bigger effective nuclear, or same effective nuclear charge. So why is fluorine bigger?
Is it the distance from the.
It's closer, right? Kind of like we talked about, yeah.
So then why wouldn't hydrogen have a higher electronegativity than fluorine?
Why wouldn't it have higher?
Yeah, because it only has one energy level.
Look at they have the same energy levels, right? Now let's take a look at the effective nuclear charge.
No, between hydrogen and fluorine.
Hydrogen and fluorine?
Yeah, because hydrogen also only wants one electron, but it only.
Actually, it doesn't. It wants to lose electron mostly. Hydrogen is the king of exceptions.
That's right.
But good thinking. All right. Does that make sense to everybody? Okay, so electronegativity value increases this way and increases this way, going up. So fluorine's the highest, and you don't have to know that if you have this table in front of you, yeah? And maybe I'll put this chart somewhere on Canvas so you can get it, yeah? And I would definitely have this when you're, now you can use this trend, sure, but does everything follow this trend exactly? We can see it doesn't, right? And then even right here, no, that follows it good. Anyway, there's some that do not follow that, but let's take a look at. In fact, let me explain how you determine whether a bond is polar or not. Okay, first of all, let's give you a little scale. And this scale is not in stone. It's not. Okay, it's kind of like a trend. But if we have an electronegative, well, let me just, I need to explain something before I talk about that scale. So let's do H and Cl, for example. what's the electronegativity value of hydrogen? 2.1. And what about for chlorine? 3.0. So which one? So electronegativity, let me give you that definition too. Sorry, I'm kind of scattered here a little bit. Electronegativity is the ability of an atom to accept electrons during a chemical reaction. Why do I say during a chemical reaction? Because it won't happen in any other way. Okay? It has to be during a chemical reaction. So fluorine wants to accept that electron more than any other atom on the periodic table. Okay. And to determine if a bond is polar, we have to find, so step one, determine the difference in electronegativity. So I'm going to call this delta E. Is that okay? Well, I don't want to call it delta E. That looks like change of energy. Let's call it delta little e. Sound good? You guys know how to find a change in anything? Final minus initial, right? Well, in this case, it doesn't matter which one's final, which one's initial. We just want to know the difference, really. So what's the difference in electronegativity in the hydrogen-chlorine bond?
0.9.
What is it?
0.9.
0.9. Okay, now we look at this scale. If the difference in electronegativity is between 0 and up to 0.5, do you understand this notation? Bracket if it includes it, parenthesis if it's up to that but doesn't include it. Okay? So we consider this to be nonpolar. And anything including 0.5 up to 1.9 is going to be considered polar. And anything above that, we would just say is ionic. Good? How do you know it's ionic, guys? Metal and non-metal. That's the easy way, right? Now, does that mean we can't have two metals with a difference of 2? No. This is not set in stone. We're always going to have things that go away from that. Yeah.
Is there a rule of thumb for where that 0.5 lies? Since it can include it or cannot include it, it can kind of go either way.
It can, and we'll talk about why when we get to molecules. Okay?
Is that not what polyatomics mostly are, like covalently bounded compounds that are ionically charged? Like have a
They are ionically charged, but we're talking about the bond themselves.
okay.
So if we have, for example, nitrate, we're talking about the nitrogen-oxygen bonds,
Oh, okay.
not the charge of it,
Right.
okay? And that's not an ionic compound, that's not an ionic bond, that's still a covalent bond.
Okay.
Good?
Yeah.
All right, so what do you think? Is this polar or nonpolar? The HCl bond. Yeah, it's somewhere right here. So this is a polar bond. And who wants to take those electrons more? Chlorine. You with me? So we say it has a dipole. and we draw it as a vector or an arrow, meaning that's where the electrons are going. So you can think of it, okay, we draw this plus sign where it's more positive, right? The electrons going that way, making this side more negative. And we say this has a partial positive charge. This has a partial negative. It's not an ionic it's not an ionic bond, so it will not have a positive and negative charge. But since it wants to pull the electrons closer to chlorine, we say it has a partial negative charge because chlorine is more electronegative. You with me? So step one is determine the difference in electronegativity. Step two is look at that scale, right? Follow the scale above. To determine if it's polar or nonpolar. And then step three is if it is polar, then assign partial positive and partial negative. And why do we do this? To help us to know what goes on when it interacts with other substances, so that we can understand the properties of different things. And right now this is just a simple bond, and later we'll get into the whole molecule. Okay? And that's really where it starts to unfold.
What is that plus and minus symbol? That letter?
This is a Greek letter delta.
Oh, okay.
Looks something like that. Looks kind of like a lowercase d with a little squiggly on it. We good? Let's try some more.
Do you mind scrolling back up to your,
Yeah, the scale?
yeah.
Yeah, let's write that down. And again, for now, this is what we're using this scale. When we talk about molecules, it still follows that scale for the most part, but we'll tell you why it might not. And it could still be polar or nonpolar, okay?
How did you assign the delta positive, delta negative for
Great question. So, delta negative refers to higher electronegativity value. If it has higher electronegativity, it's going to bring the electrons toward it more, making it more negative. Does that make sense? Because the electrons are negative. And a partial positive refers to the lower electronegativity. Does that make sense in your mind? It's a bigger electronegativity, it has more electrons near it, therefore more negative. But it's not like an ionic bond where you have one side's positive, one side's negative. It's not like that. Good? Oh, that was our break call, wasn't it? I forgot. Turned it off and then. All right. Yeah.
Just like the bottom.
Oh, scroll up.
Just like the 1, 2, 3. You just want to
In the class, I feel like I'm out of heat stroke. Actually, missed the SI basement. Oh, yeah, it's cool. I thought I'd say that.
Hey Seth, how's it going? Did we getting real chem in? Did we able to get that?
No, I just haven't navigated through it yet, I'll do that.
Okay.
Thank you for checking.
Let me know if there's anything I can do.
Appreciate that, thank you.
Yeah. Sorry, that probably
It's all good.
threw off your nap zone, huh?
I saw on the course schedule, like the
So we for sure get it this time. Gosh. Let's do a few examples and then let's put them in order of. In fact, first of all, why do we deal with polarity? This is chemistry, and this is what they do. No. So sometimes we think that, right? But eventually we're going to get into the molecules and determine if the molecules are polar or not. So who cares, right? Well, let's take a real life example of this. We just cooked up some meat and now it's all greasy on our pan, right? And we got to wash our pan. We'll just put it under the water. Hot water's better, right? And just, it'll come clean, right?
It's hot enough.
Or will it still be greasy and slimy? Yeah. If you ever wash dishes, you need what? Soap. Oh, okay. Well, how does soap, does soap mix with the oil? Kind of does. It mixes it up and takes it away, right? Does oil mix with water? No, it does not at all. Does soap mix with water? Well, that's weird. Soap can mix with both oil and water. That's because soap has part of the atom, part of the molecule is polar, and part of it is nonpolar. Oil is nonpolar, and water is polar. That's why they don't mix. And so the takeaway here is like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. So that's just one application. It helps us to understand, well, first of all, we need something to get rid of this oil. That's why we come up with soap. Okay? Find something that has both properties. And we'll talk more about it as we get there. And then we use this difference in polarity to determine, okay, well, how strong are these molecules held together? If they're held together strongly, then it gives them these properties. If it's not held together very strong, it gives them these other properties. So it helps us to recognize or to predict the properties of different substances. Does that make sense? Kind of ish? And we will get there as we go along. But that's why we're dealing with polarity. All right, so let's do a few examples. It's recording. Good. So the CH bond. and the CN bond. Should we do one together, or can you do these yet? Together? All right. So the first step is determine the difference in electronegativity. What's the electronegativity value? Oh, we got to pull this up, right? What's the electronegativity value for carbon? 2.5, and for hydrogen is 2.1. So 2.5, 2.1. What's the difference in electronegativity? 0.4. Therefore, it is nonpolar. So which one's partial positive and partial negative? We don't worry about it. Now, is there a difference in electronegativity? There is. So that means they're not sharing 100% the same. If we had, let's say, a carbon-carbon bond, that would be 0 in difference, right? So that's absolutely nonpolar. So there's a slight polarity here, but it's negligible. It doesn't really tell us that it's polar as far as like dissolves like, okay? So we call this nonpolar. We don't have to worry about which side is partial positive, which side is partial negative. That's nice. What about this one here? This is still 2.5, and what's nitrogen? 3. And the difference is 0.5. So what is it? Barely polar. Okay, they're really close to the same, right? So I guess that's the threshold of polarity. But so for our, we're just going to say it's polar because it's in that range. Good? If it is polar, what do we got to do? Determine which side is partial positive, which side is partial negative. I like to start with the partial negative. Which one is partial negative? Carbon or nitrogen? Nitrogen is partial negative because it's more electronegative. You with me? Partial positive. So if I draw a dipole, it's going to go this way. Meaning the electrons are going to go toward the nitrogen. You with me? All right. Any questions on how to do this? Yeah.
What's the deal with your vector that you draw?
It's just saying what direction the electrons are going toward.
Oh.
So we call it a dipole. And if we have a dipole, then we can have, kind of like we can rub that balloon and stick it on the wall, right? Okay. It's not really charged, but, so let's see. How does it stick to this wall? Is this wall charged? It's not. But what happens when you charge that balloon? It rearranges the electrons in here a little bit to cause it to stick. And that's the difference in polarity. But anyway, that's kind of what a dipole is. It's kind of an attraction to help these electrons go one way or the other so that they make that, yeah.
Does finding the dipole moment, does that help determine polarity?
Yeah. Yep. Yep. And let's see, I don't know how deep we go into this. We may or may not get to that. Okay. So let's try a few examples. And I want you to put these in order of lowest polarity to highest polarity. Or the strength of a polar bond. Okay? So we got HCl. We got CHOF, CN, NaCl and FCl. So we got to determine which one is more or less polar. How do we do that? Should we try it on something that we already did? This one and this one? Which one do you think is more polar? The HCl bond or the CN bond? Why is that? Greater difference in electronegativity. That's it. So if we were to draw these, so the HCl bond would have a dipole like this, and the CN bond would just have a smaller dipole. We draw the length of that arrow to represent that strength and polarity. Good? So why don't you try this? Now we can do this together, we can. But until you can do this, then it doesn't matter. Yeah.
Did you ever do this between three elements?
Like a compound where it has, yes, and that's where we're getting. But right now we're just keeping it simple.
Will you move it back up, please, to the chart?
Oh yeah.
Like, on a test, would we be given this chart?
No.
So we have to memorize?
No. I would put this on your reference sheet. In fact, would it be useful if I just printed you a copy and you had it? Okay.
Or upload it like as a
I'll do that too.
Yeah.
These, the ones that'll be on the exam, set ones with like slightly more specific, electronegativity numbers.
Yeah. These could be, this is just one I pulled from Google. And just like the periodic table of the atomic masses, you get one periodic table that says carbon or oxygen is 16 and some that says 15.99. What is it? Ish. Right? So this scale is just on a scale from 0 to 4. And someone just, it's an arbitrary scale. Okay, so 4 is the biggest. That's why fluorine has a 4. And what about helium? How come it's Na up there? It's a noble gas. It doesn't want to take any electrons in. So it basically has a 0 electronegativity, right? Yeah.
For the KR and XE, why do they have an asterisk next to them?
Because depending on what it's with. Because, so xenon will bond to other atoms. There's always exceptions, right? Darn exceptions. Yeah.
Is there a way to directly calculate the electronegativity without using the chart?
I don't know. There might be. In fact, they had to get these numbers somehow, right?
So we have to.
Just me about that.
But maybe they just tested it and says, okay, this one's stronger, we're going to call it a 4. It's the strongest one we saw, so we're going to call it a 4. I really think it is that way, but I don't know for sure. Yeah.
So we have to put that on our reference sheet?
I would if I were you. You don't have to.
I mean, how are we gonna get numbers if you don't?
Yeah, if I were you, I would.
That's
And you can shrink it down, and
it's gonna take so much space.
it doesn't have to. Did you guys see my reference sheet that I put on the home page? You can look at it. This is on, I think it's on there. Maybe it's not. I think it's not because
No, just the periodic table.
for that class, I gave him this chart.
Can we tape it on there, or we have to draw it by hand?
You have to draw, and it has to be in cursive and, no. No, yeah, I would just shrink it. In fact, the way I made my chart, my reference sheet for the example that's up there, I did it all on Microsoft Word, and then just printed the sheet out. I didn't write any of it by hand. I found stuff on the internet, pulled all the stuff to make it easier for me, and then just printed it out. Yeah.
So it would be more helpful to have this on our reference sheet, and the question would never just give us the numbers. Like the question would be like,
I wouldn't say it would never, but
there's a possibility of just without.
yeah, I would definitely have this on your chart. You can make it small, make sure it's big enough to read, but okay. Did we not do this because I had this down, or? Okay, so this one right here, we had a difference in electronegativity of 0.9. We just did that one, right? And this one we already did is 0.4. What's OF? 3 point, it's 0.5. CN is 0.5. NaCl 2.1, and FCl 1. Okay. So what's the lowest in polarity? The CH bond. Then the OF bond, which is equal to the CN bond. Then the HCl bond, the FCl bond, and NaCl. Well, we don't really call that polarity. We don't call it a polar bond because it's an ionic bond. But according to this chart, sure, ionic bonds are highest in polarity if we want to call it that. But in general, we don't call ionic bonds polar bonds because they're just positive and negatives, right? Full positive, full negatives, no partial negatives, partial positives. Are we good? Okay, that is all I have for you today. Unless, we'll just keep it civil this weekend. Let's just be done. And then, so there you can. There's a little bit of practice on this worksheet that you picked up that you can do so far. And that is section 1 and section 2. We'll do the rest later, next week. Any questions? Thanks. All right, that's it.